Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am very pleased to have Hannah Diamond-Lowe with us today. Hey, Hannah.
Hi.
Where are you at?
I am a little bit north of Copenhagen in the Kingdom of Denmark.
Ooh, oh, kingdom.
Yes, technically, I think that's correct.
Is it actually a kingdom? Is there a king and a queen? And all
There's
that?
a queen. There's a queen, yeah.
Why do we call it the kingdom then? We should call it the queendom.
This is
a
good point. This is a good point.
Is there usually a king, or we just don't happen to have a king now? Or is it always a queen?
Oh, wow. So my Danish history. No, there have been kings. It does so happen at this point in time, there's been a long reigning queen, Queen Margaret. Yeah.
Very cool. Very
yeah.
Good. Let's see. It is September 30th, 2021. We are recording this, and so we've gone through equinox about a week or so ago. So is the weather started to change there in Denmark? Do you have 5 feet of snow yet? Can you see the Aurora Borealis?
Well, it doesn't actually snow that much in Denmark and in Copenhagen. We get a warm air current from the Atlantic, but it is currently raining, and it does that quite a bit. Okay. So yeah, fall has arrived.
Fall has arrived. All right, there we go. And fall has arrived here in Phoenix as well. It's a little unusual, but yeah, right around equinox is when the power switch went off, and so we went down into maybe the 30 Cs or something like that, which is
cool.
Yeah. So yeah, we're doing well there. So you're obviously in your institutional office there.
Yes.
So is everybody coming back into the office these days, or is it still kind of restricted, or how's that working?
We are fully open for business here. So, okay. Yep. Cool. Yeah. Yeah. It's nice.
Yeah. Hannah, what do you like to do for research?
Okay. So I am primarily interested in small exoplanets. So these are exoplanets smaller than, about the size of Neptune, and all the way down to terrestrial planets, which are sort of more, think your Earth, your Venus,
right,
Mars. And what I'm primarily interested in is their atmospheres, because after we've measured their sizes and their masses, the next best thing you can learn about is what is in this little shell around them that we call an atmosphere. Do they all even have atmospheres?
Yeah.
And there's a few ways we can study this. We can, of course, try to look for those atmospheres, which is something I've done. But a little more pertinent to the paper I'm going to be talking about today, we also want to know what the radiation environment that they've experienced has done or is doing to their atmospheres. So of course, I'm talking about the host star. And the small planets that we're really able to detect and study orbit these small stars called M-dwarfs. Yes. These M-dwarfs are different from the sun, and so we want to learn a little bit more about what they're like.
Cool. Very nice.
Yeah.
That is an awesome research program. And that is going to bring us to this very lovely AJ article on the high energy spectrum of the nearby planet hosting inactive mid-M dwarf LHS 3844. And Hannah, take us away.
All right, thank you. Yeah, so as I said, this is going to be an investigation into the host M-dwarf star of an exoplanetary system. So the star has a known exoplanet around it. I'll tell you a little bit about that planet, but we're mainly going to focus on the star. And as I tried to squeeze all in the title, this is considered an inactive mid-M dwarf star. So not a lot of flaring. It has a relatively slow rotation period of about 130 days. So we're not looking for, this is not, like your AU-MIC or your Epsilon Eridani, for instance. Mm-hmm. Okay, so how did we study this star at high energy? We've mainly used UV observations from the Cosmic Origin Spectrograph. This is called COS, which is aboard Hubble, HST. And we've also used some soft X-ray measurements from SWIFT. And this, we did not get a detection in SWIFT, but we can use it to place some upper limits. And so what this paper is going to do is explain how we construct this high energy spectrum from the UV measurements, from the X-ray measurements. And a key component of that will be how we use those two measurements to access parts of the spectrum, parts of the high energy spectrum, which we can't actually measure directly for various reasons, which I can explain as we go.
Cool.
Yeah, so that's, yeah, I guess let's get into it. So if we sort of just stay in the introduction, I do want to introduce the system a little bit. So LHS 3844 is a nearby star. It's about 15 parsecs away.
Okay.
And it hosts, as far as we know, one exoplanet called LHS 3844b. And we know from the radius of this planet that it is terrestrial in nature, so it's very small. We think it has a rocky composition. And from a few other measurements, we also suspect that this planet, which is very highly irradiated, does not have an atmosphere. Yeah, so the planet parameters are in the second half of this table. You can see it has a radius of about 1.2 Earth radii. We would consider that terrestrial on the sort of terrestrial side of the small planet radius valley.
Okay, I'm with you.
Yep. Yeah, so some measurements show that this planet does not have an atmosphere. So we can kind of ask, well, what does the star look like such that it has been able to strip this planet of an atmosphere, and maybe what time scale did that happen on? So we'll be able to sort of explore those questions with the high energy measurements of the star.
Cool.
While I think if you scroll up a little bit,
Sure.
I just want to introduce a few terms here. Okay. So kind of in the middle of the page, I talk about the far ultraviolet and the near ultraviolet. So we're talking far UV, FUV, that's 912 to 1700 angstroms. The near ultraviolet is 1700 to 3200 angstroms. Okay. And then you go even higher energy, you get to X-ray. X-ray is 1 to 100 angstroms, or that's what we're sort of defining it as here. And then you have this extreme UV, the EUV, which fills in that gap from 100 to 912 angstroms. And there'll be some figures where you can kind of see this more clearly. Okay, so what happened first? So I think if we go down to our first non-introductory section, it talks a bit about the ultraviolet measurements that we made of this star, LHS 3844. So we used 10 orbits of HST with COS to look kind of across the UV spectrum from the far to the near UV. And there's some details here about what settings we used. But if we go to Figure 1, you can kind of see a time series of the observations. So this is going to show sort of what we were observing in each orbit. And I've kind of plotted it out here. These are the counts per second, and you can kind of count, there's 10 little panels here. Those are the 10 orbits that we used. And what we saw right away is in that top left panel, if you pay attention to the dark blue points are the binned down time series to about 10 minutes. You see there's a little peak and a slope down there. Yep. And that is a textbook characteristic flare.
Bang. Yep.
So
Okay.
I pulled this up and I was like, oh, wow, so cool. There's a flare. And then I thought, oh, no, now I have to do a bunch of stuff to figure out, what is the flare, the energy, and what does it all mean? But it was also pretty exciting. So we can actually get a better picture of that in figure 2, I believe it's, yes. So we'll do a little zoom in here.
Yeah, very cool.
Yeah, so I've taken just that one visit and I've highlighted in orange where these flare points, and then we've fit this model by Jim Davenport to the flare. That's what's in red. And from that, we can determine some properties of this flare. There is how long it actually lasted, and then we can also measure what's called the equivalent duration and the equivalent energy. This is sort of a normalized version. It's kind of analogous to equivalent width in stellar spectra, but it lets us then compare two flares in other stars.
Okay.
Yeah, this was a small flare. We would consider this this is not a big, Carrington event type situation. This was a small flare, but nevertheless above our detection threshold, so we could see it.
Very nice.
Yeah, and then what we decided to do here is to actually cut out this flare from the time series. And separate the spectrum from just these flare points, as opposed to the spectrum that we would consider quiescent. So that's all the other blue points. So what I'll just say is, this is the time series, but when we go to construct the stellar spectrum, we collapse all of these and because we're just building up signal in wavelength space as opposed to time space, which you're seeing here. So adding in this tiny flare isn't actually it's not going to make a huge difference, but we wanted to separate out the flare to actually see, how much flux is coming just from these few flare points. Is it the same or is it different from the quiescent spectrum? Yeah. So I think if we go sort of down to which part, where are we at here?
Table 3, figure 2, talking about the properties of that flare.
Yeah, let's go. There should be a table, I think table 4.
Table 4, let's take a perusal.
Yeah.
Table 4, measured line emission characteristics.
Yes. I think that's right. There's a bit of a delay in my screen.
Okay,
perfect. Yeah. Yes. Table 4. So this is, I don't want to go into all the numbers because it is a table, but what you can basically see in the columns that say log surface flux, and then there's another column, log surface flux. The first column is the quiescent spectrum. So we've removed the flare in order to measure these emission lines. And you can just see by eye that in the lines where we measure the flare, so we only detected it in this one grating. So where we detected the flare, they're about an order of magnitude more flux in the flare for these measured lines, which is pretty cool. So now if we actually go up to the figure just above this, you can actually see what this looks like. So these blue, this is the now quiescent spectrum. Okay. You can see kind of how noisy these data inherently are. This is an M-Dwarf 15 parsecs away. It's not emitting a ton at blue wavelengths, but we are nevertheless able to see these signals, which is really cool. So we measure the measured data is the sort of lighter blue squiggly line, and then we fit a kind of Gaussian curve convolved with the line profile of the instrument. And that's how we're determining, then we can integrate under this curve and determine the line strength. If you scroll down to the next figure, we'll have the same thing, but for these emission lines measured during the flare, and you'll see they are quite noisy and the fits are not quite as pretty, but nevertheless, this is kind of the best we can do here. So they're stronger, but a lot noisier. So we actually are able to now compare, quiescent star to flare star, kind of. It's a very rough estimate. And we're gonna continue with the quiescent and the flare examples throughout the paper.
Okay, great.
Yeah. Okay. So that was sort of the surprise of this project. We weren't expecting this. And so after we do all this work, okay, now we get back to the real project, which is constructing a high energy spectrum of this star LHS 3844.
Okay.
And the first thing we have to do is think about Lyman alpha. So if you scroll down a bit, yeah. All right, this equation 3, let's kind of have that hanging out. So there's, COS is a great instrument because it has quite a lot of throughput. And for a star that's dim in the UV, like this one, that's a huge asset for us. We want to use this a high throughput instrument. Unfortunately, or sort of for the same reason, COS is a slitless spectrograph. So you just take the COS aperture, you put it on the sky, whatever comes in, comes in. Unfortunately, that means that in the Lyman alpha region, which is a very strong emission line for a star, we actually, there's the construction. We actually get contamination that is not at all from LHS 3844, but it's from solar photons interacting with neutral hydrogen in Earth's atmosphere.
Okay.
So in the raw data, you get this huge Lyman alpha signal, and most of it's just from the Earth. We don't want that. That's not helping us. So what people have done is actually used another instrument aboard HST called STIS. STIS does have a slit. You are able to get low contamination from the Earth and measure parts of the Lyman alpha flux. However, this star is simply too dim. It would take something like 70 orbits with HST and STIS to do that measurement. No one's going to give us that time, I think, understandably. So we need another way around this. And the way we're going to get around this is not observationally, but we're going to stand on the shoulders of the Mussel survey, which was this really great survey that looked at a bunch of M dwarfs and measured their properties using COS, using STIS, looking at them in X-ray, and they have a really wonderful library of M dwarf stars. What they found is that no two M dwarfs are alike. They each have their own, even ones that you think might be similar effective temperatures, seem to have very different signatures in terms of their high energy profiles. But there are quite good correlations between one emission line and another emission line that seem to hold throughout the sample. Okay. So this line strength, and of course you have to normalize by the distance to the star and the size of the star, but once you normalize, the line strength of silicon-4 correlates well with the line strength of carbon-2, and this correlation is quite good even across this sample from M0 down to, I think, M5 or M4. And they, because they were able to use the STIS instrument to actually measure and reconstruct the Lyman alpha lines, they also provide correlations between the Lyman alpha line, the strength of that line, and the strength of other lines in the UV, for instance, silicon-3, carbon-2, these ones that we were able to measure. Cool. So we're taking our measured lines and using the UV-UV correlations in order to back out an estimate of the Lyman alpha flux that we weren't able to measure for LHS 3844.
I'm with you. Yep.
Okay, great. So this equation 3 is from this great paper by Allison Youngblood in 2017, and it is the simplest linear function But the fact that it actually works, that there is this linear correlation, I think is really, really
Pretty interesting.
amazing, one of these like thank you nature situations. So we have, you take your surface flux from one UV line, and you can get to that if you have the slope of the correlation M, and of course some y-intercept B. And these values are provided in Youngblood 2017. You can go and use them yourself. If we then scroll down to this next figure that's kind of peeking up from the bottom there. Yes.
There we go, figure 5.
Yeah. So we applied this equation 3 to the emission lines that we do measure. And so those are on the x-axis here, silicon 3, nitrogen 5, and so on and so forth. And this bar graph with the error bars, at least the blue bars, correspond to the Lyman alpha surface flux, or the log of the Lyman alpha surface flux for LHS 3844 that you get from correlating with silicon 3, with the silicon 3 emission. And then again, what do we predict based on nitrogen 5? And so on and so forth. And as you can see, there is good agreement within the error bars across the measured lines, and which is somewhat expected, right? Because these are based on correlations across the sample. We already know these correlations are there, but it's nice to see the comparison working out. And then we can do a sort of an average across these, and the very last bar, this kind of lighter blue bar, that is our estimate for the Lyman alpha flux of LHS 3844 in quiescence. Yeah. And then we've done a similar yet slightly cruder thing for the flare spectrum, because we only measure a few lines. You get a nice correlation, but it's not as certain that Lyman alpha is responding the same way during a flare. We're not sure about that. But for the argument of just sort of seeing where this goes, keeping our 2 spectra, we're gonna make that estimation. Okay. So now we have our ultraviolet spectrum, including the very important Lyman alpha line. And now we have our next gap, because we cannot measure flux in the extreme UV. So if we scroll down a little bit.
Equation 4, table 5.
Let's go to the next figure. Okay, yes.
Figure 6.
Yeah. Nice. So these, I'm not going to get into all of the panels here. They're just sort of comparing different methods for doing what I'm about to say. But the problem is that between 100 and 912, well, out to 1,000 angstroms, we don't have any measurement of the star. And actually, we cannot have any measurement of this star because there is currently no spacecraft that can make observations, especially from about 400 to 912 angstroms. There were a couple that ran sort of in the 90s into early 2000s that could do this, but you're still running up against this problem of, as you're approaching 912 angstroms, which if you recognize that number from the Lyman alpha continuum, you're more and more of your flux is getting eaten up by the interstellar medium. So, even if we could build a telescope that could observe at those wavelengths, you really wouldn't see much except from the sun. So we need some ways to fill in this part of the spectrum. There have been methods that use sort of, again, a kind of correlation method, but we wanted to use something a little more state of the art, especially because this is an M-dwarf star, and these correlation methods have worked quite nicely for sun-like stars. And they have been applied to more active M stars, but this is sort of, we wanted to see if we could do something a little bit better. And what we did was very fortuitously, in terms of timing, there was a paper by Girish Devori, who took what had been developed in the stellar astrophysics community, and he kind of helped translate it for, people from me coming from exoplanets. So what can we actually do with these high energy spectra so that we can like get a good estimate out of this wavelength range. I'll explain a little bit about how we do that, but I'll start just here with this result in figure 6. So the panel all the way over to the right is our, this is our estimate for using this new method that uses what's called the differential emission measure. So we use this method to estimate the flux in this range. The blue is the quiescent estimate, and the orange is the flare estimate, and the kind of different shadings going on there are we try a bunch of different assumptions, and we kind of show that it stays about within the right order of magnitude, or even less, within a factor of a few in some of these bins. Okay, so how are we doing this? So if you scroll down, there should be an equation. Let's see.
Damn. Okay.
Yeah.
Pull it out a little bit. Down, possibly up. How about? Possibly
up. I'm trying to find equation 4, if you can find that. Yeah. Yes. Okay, great. So if, and I really will say, if you want like a very good in-depth explanation for how this method works, I really encourage you to read this Devori et al. 2021. It's a very nicely written paper, and it really explains well how this works. But I'll just get into it basically, which is we take this equation, equation 4. So it is the intensity with this little UL, which is sort of a notation for upper lower. So we're really talking about an upper to lower transition and the energy that gets released from that. And it's the integration over temperature, that's T. And then there's these two functions. So this G and the UL again for this transition, the G is the emissivity contribution function. That's going to be something that we actually get out of a database. And then you have this capital psi, which is also a function of temperature, and that's the differential emission measure. That's the thing we actually want to get from the data we already have. Okay. Once we have it, we're going to use that function again with the G function, which we get from a database, and we'll actually get out the intensity of transitions that we don't measure directly.
Got it.
Now that seems a little bit wonky, like how does that math work? And this relies on the fact that this emissivity contribution function is actually concentrated, the bulk of it is coming from a very narrow temperature range. Yeah, so it's not really a delta function, but it's close, in which case you can basically say that, well, the differential emission measure for a particular transition, for a particular, ion emission, is only really valid over a narrow temperature range.
Okay.
Yeah. So let me show you the result of that. So if you scroll down to figure 7.
Yeah, it's a little too big. Let's try that. Okay.
Yeah.
Yes.
Nice. Okay. So this is the results of our we're getting now the differential emission measure and then fitting a curve to it that is the function. So we've gotten the emissivity function from the Chianti database, which is this really, really nice database that has a lot of tools. If you're interested, you can look that up as well.
I can't think.
Yeah. What we've done is taken the lines that we've measured. So we've measured them, so we can just calculate the intensity.
Mm-hmm.
We have taken their emissivity contribution functions, which we just put in a few stellar parameters, and this does assume a optically thin plasma, so it's only really valid for the hottest parts, the chromosphere. This wouldn't work for the photosphere of the star. And you can see that I've put the differential emission measure that we get for these emission lines, which we do measure, and I've plotted them as a function of their peak formation temperature. So that's the peak of where this emissivity function happens.
Mm-hmm. I'm with you.
Okay, and the argument here is that these emission lines, so for instance, carbon-3 or silicon-4 or silicon-3, because they are sort of concentrated at a certain temperature, we can then predict the concentration of other ions form at a similar temperature.
Okay. Mm-hmm.
So this is sort of the crux of the argument.
Got it.
If you focus on the blue points, those are the measured intensities from, or we have the intensities of those from the UV spectrum and also from the X-ray, or that's an upper limit on the X-ray over there. And we can now fit a sort of simple polynomial function to these points with a few constraints. The function has to go, up at lower log temperatures and down at higher ones. And we sort of put some parameters in there when doing the fit.
Monotonic.
Yeah. But basically you get out this smoothly varying function. That light blue dotted line that you're highlighting. So now that we have that function in hand, we're gonna use that function along with the emissivity, the G of T function of transitions that happen where we can't see in that extreme UV region, and we're gonna get out an estimate of those intensities.
Okay.
And that's kind of that's the result of that is the figure we were looking at just before. So it you sort of like go down this equation one way and then go back, and that's kind of how we're getting to the extreme UV of this star.
Yes.
Yeah.
Okay. I'm with you. Yeah.
Okay.
Cool. Nice.
All right, and that's how you build a high energy spectrum. So the next figure down, figure 8 should be, is the kind of putting it all together of this. And you'll see that with all this work, this is a tiny part of the spectrum, but it's really, really important. So this is in log space here, which is why it looks a little silly, but we want to highlight the high energy. You have here if we just talk about the quiescent region, we have an upper limit from the X-ray observations between about 100 and 1,000 angstroms. You can see that's the extreme UV part of the spectrum. That's what we put all this effort into using the differential emission measure to actually get those estimates in. You can see there's right past 1,000 angstroms, there's a high blue point.
Yep.
Right there, that's the Lyman alpha estimate. Yep. So it's just this one line, but it makes up a huge portion of the UV. So that's why we're so careful to get an estimate of that in there. And then we've just sort of appended onto that a Phoenix model for this star so that we have something going from all the way from 1 angstrom out to 10 to the 5 angstroms. So a real panchromatic spectrum. Yeah. And finally, I just want to highlight what we have done with this spectrum and maybe what could be done going forward. So if you scroll down to the very last figure, figure 9.
Last figure is 10.
Oh, sorry, figure 10. Just kidding. Figure 10. Yeah, we're going to skip figure. That's fine.
Yes, yes.
Yes. So we worked with some really great folks at University of Maryland who work on these photochemical models. And as I sort of mentioned at the top, my real interest, or my real driving interest, I should say, are the atmospheres of small planets. And if we want to understand those atmospheres, we really should have an idea of what is happening with the photochemistry. So that's any chemistry that's kind of occurring because of input radiation from the host star. And primarily, the primary source of radiation that can really break apart atmospheric molecules and let them reform as probably maybe some other molecule is the UV. This is happening in Earth all the time. This is actually how we get ozone in our own atmosphere. UV energy from our sun breaks apart oxygen. We get ozone. It's very important for us because it prevents a lot of bad UV from getting to the surface. So I'm interested in thinking about atmospheres like that for exoplanets. So I was able to give the product spectra that I came up with from the quiescent and the flare cases to the photochemical modelers over at University of Maryland. And they came up with a toy case, which is, so they've taken the planet and they've just kind of moved it a little farther away so that it receives the same amount of insolation as the Earth. So this is not a real planet, but we've taken the real planet, kind of moved it farther away. This is primarily because these equations were developed for an Earth atmosphere. So because this is a sort of exercise in how we can use stellar spectra, I didn't want them to, reinvent the wheel. We're just going to kind of take an example case here. Okay. And in the left panel of figure 10, the black curve is the temperature pressure profile for this made up planet's atmosphere. And you can see it's pretty similar in the quiescent case, which is solid, versus the flaring case, which is dashed. But if you actually look at the mixing ratios of the molecules in this Earth atmosphere, especially at low pressures, so high altitude, you can really see a difference in how much of that molecule is present.
Yes.
And it kind of makes sense that during the flare, when you have perhaps more UV energy in the far UV, you're going to be breaking apart things like CH4, that's the pink curve, or water, which is the purple curve. And this is, this wasn't a full exploration. So, we might be interested in how long the atmosphere might be in this state before it returns to maybe a base state. But the point is, these are real differences happening because of the photochemistry, which we can actually calculate with this empirical input that is the stellar spectrum that we measured.
Okay.
Yeah. And before we get too excited about that, in the left, the right panel here, we can see that this is the computed transmission spectrum. Okay. That we, again, would see. And you can see even in the quiescent, the sort of blue case, that was when we put the quiescent stellar spectrum as the input versus when we put the flare stellar spectrum as the input. Okay. You're not going to see a ton of difference in transmission. So there is definitely advances we can make observationally before we can really say is this planet's atmosphere, has there been a lot of flaring activity that has changed the photochemistry, or maybe not. But I am very interested to see if these M-Dwarf spectra, which we've, taken great pains to measure and then sort of build up all these different pieces, and we really want to see how these are affecting the photochemistry in planetary atmospheres. And this can have an effect on the molecular production. It can also have effect on the haze production. We know a lot of these small planets have hazy atmospheres. We think this is because of photochemistry, but to what extent that's happening is still, I think, a pretty open question, especially from, an observational perspective.
Awesome.
So I think I'll leave it at that.
Cool.
Yeah.
Very nice. Very nice. Thank you so much for walking us through your very lovely article. And you hit on it a couple of times there toward the end. So is there, any specific 70 HST orbit things going around to get additional data, or are there new observational capabilities coming online? Maybe Vera Rubin or something along those lines, new missions going up. Is there additional theoretical calculations, maybe beyond toy, that could be done? And just sort of, where do we go? Where does the community go over the next 5 years? And you don't have to spill your next research project if it's related, but you could if you wanted.
Sure, no, absolutely. So I'll just touch upon, because you mentioned, other observatories, and I think something to really drive home is HST is really the only observatory we have right now that's capable of making these ultraviolet measurements at the precision where we need for these M-dwarf stars. So it's really vital, I think, to be gathering as many of these spectra as we can while we can. And I think there's a few reasons for that. One is that these M-dwarfs, we do know that they do look pretty different at high energy. And what I'm really interested in is actually doing, a more bespoke understanding from, this is what we know the host star looks like. We have these planets. What is actually going on here? How is the stellar high energy spectrum affecting this planet's atmosphere? And, is this a planet where we might expect to actually see features in the atmosphere? Or do we actually suspect that, this will be a very hazy planet, we might not actually be able to see anything? Because we're only going to have so much JWST time, so much time on the upcoming ground-based telescopes. We want to be targeting those planets where we can actually see something. And if we ignore what's happening with the photochemistry, because we don't know enough about the star, that might hinder us in picking those best systems. So I am sort of doing similar work like this for the K23 system, which has 3 planets in it. We're hoping to kind of pair the UV observations that we have with a sort of more relevant modeling effort that's actually going to be able to look at the planets as they are, kind of move them around, which is harder to do. But we're going to try to see what if the planet looks like this one end member case, what will its atmosphere look like because of the stellar spectrum? If the planet's instead this other end member case, what does the atmosphere look like as a result of the stellar spectrum? So that's kind of in the works. And I've also gotten some time on HST to look at 2 other really nearby exciting M-dwarfs and kind of do a similar thing. Yeah.
Yes, very nice, very cool. Well, I look forward to seeing your future work on this topic as we seek to characterize these kind of systems at these energies. That is totally awesome. Cool. So Hannah, thank you once again for walking us through your really lovely article. And that'll do, everyone. And I hope this makes your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.
Bye. Thanks for having me.